Good
Morning, sir.
morning.
Sir, I had a question.
Yes, please.
Sir, can we have classes on Wednesday and Friday instead of Tuesday and Thursday?
Right now we are having on Wednesday and Friday,
Oh,
no?
sorry. I meant to ask to the other professor. Okay. Sorry.
Okay. Okay, let's start. So, what did we do last class? Last class, we talked about subsemi groups, submonoids, etc. And then we observed that substructures are preserved under morphisms and inverse morphisms. And then we talked about congruences and quotients. And I asked you to prove the first isomorphism theorem. First isomorphism theorem. Okay, which was that if I have an S and I have a morphism phi to T, and if I quotient S with respect to the nuclear congruence or the congruence induced by the morphism on S, then there is a canonical map from S to S slash tilde phi, and then there is a morphism pi prime from S slash phi to T, which is a isomorphism. Yeah, this is what is first isomorphism here. Do you try proving it?
Yeah, I could prove it.
Okay, all right. So now let's continue. So I will also state what is the second isomorphism theorem. So isomorphism theorems are standard statements uh, in any definitions of algebra. Whenever you have a notion of an object, whenever you have notions of quotients, and whenever you have notions of, well, if you have a notion of an object in an algebra, and then you can define a corresponding notion of morphism, corresponding notion of quotient, and then you will have a standard isomorphism theorems connecting all these three. Yeah. And so typically they are stated as statements of universal algebra. But when you study group theory or ring theory or any of these things, you will start with these basic statements. So what does the second isomorphism theorem state? So second isomorphism theorem, I'll not prove it. I'll leave you to as an exercise. These are not hard statements. These just follow from the definitions of the objects we deal with. Okay. So what is the second isomorphism theorem says? Let S be a semigroup. Let tilde 1 and tilde 2 be congruences on S such that uh, tilde 2 is coarser than tilde 1. What does this mean? Somebody? What do you mean by coarser? An equivalence relation is coarser than another equivalence relation?
If A and B are congruent with respect to tilde 1, then they will be congruent with respect to tilde 2.
Exactly. Okay. So in other words, what it means is that an equivalence class of tilde 2 is made up of equivalence classes of tilde 1. Yeah. So if you consider equivalence classes as pebbles, then tilde 1 pebbles are tilde 2 pebbles broken into pieces. Or in other words, tilde 2 pebbles are made up of are bigger than tilde 1 pebbles. Yeah. That's why the no the, the that's why you call it coarser and finer. Yeah, one is finer pebbles, one is larger pebbles. Okay. And let pi 1 and pi 2 be the canonical morphisms from S to S slash tilde 1 and S slash tilde 2 respectively. Okay, so what is the situation? You have S and then you have two morphisms, S slash tilde 1 and S slash tilde 2. And this is this morphism which maps an element in S to its corresponding equivalence class in tilde 1 is called pi 1. This is called pi 2. Okay. And you know that tilde 2 is coarser than tilde 1. So there exists, so and what is second isomorphism theorem says? There exists a morphism pi from S slash tilde 1 to S slash tilde 2 such that, so there exists a morphism from here to here pi such that pi 1 pi composition pi 1 is equal to pi 2. Okay. Yeah. So there is a morphism from S slash tilde 1 to S slash tilde 2 says that if you look at this morphism, which is obtained by pi 1, pi composition pi 1. So another thing which you have to notice that Composition of two morphisms is another morphism. Yeah. So if you have pi, composition pi1 will be equal to pi2. Okay. All right. So this is an exercise. Prove second isomorphism. All right. Okay. Now,
One question.
yeah.
So then what is the isomorphism here? Or is there, why is it an isomorphism theorem?
Why is it an isomorphism theorem?
Or is it an isomorphism? Is pi an isomorphism? Not
No,
necessarily.
no, no. Pi is not an isomorphism theorem. Pi is not an isomorphism. I don't know. Why is it called an isomorphism theorem? Interesting question. I never thought of it actually. Let me answer you it in the next class. Yeah, I have to.
Yeah,
think.
yeah. Okay. Okay, sir.
Okay. So maybe in another formulation it could be stated as an isomorphism theorem. Yeah.
Yeah.
It may not be this formulation. Let me think about it.
Okay, sir.
I'll tell you in the class.
Okay.
Okay. So next thing. So I was talking about a semi-group congruences, and there is an interesting way we will use semi-group congruences. Okay. So I was giving you one example of semi-group congruences, which was congruences induced by quotients. Now, there is another interesting way in which semi-group congruences are used, okay, which will be useful for us. Okay. And that is, let's imagine I have a symmetric binary relation R on a semigroup S. Okay. So I have a symmetric binary relation, a binary relation that is symmetric on a semigroup S. Now I can define the smallest congruence containing R. Okay. And what is the smallest congruence containing R? You look at all congruences which contains R and you take its intersection. Okay. You take the intersection of all those congruences, that will be a congruence. So here I have an exercise. Show that intersection of congruences is a congruence. Okay. Intersection of congruences is a congruence. So probably let's put it finite number of congruences. Intersection of two congruences is a congruence. Okay. And okay. So now the smallest congruence containing R. Now there is a way in which this is useful. So I'll first explain what is this idea. Let's imagine I have an alphabet A, B. Okay, I have an alphabet A. Now I look at all. I take a binary relation like AB equal to 1. Okay, so what do I mean by AB equal to 1? I mean AB 1, the relation AB 1 and 1 AB. This is what I mean by AB equal to 1. Okay, so I look at the my monoid is A star, and I look at binary relation R, AB1 and 1AB. 1 is actually the empty word, the identity. Okay, I'll be using the name 1 for the identity. Now, what is the smallest congruence containing R on A star? What is the smallest congruence? Now, let's imagine what is the smallest congruence containing R. Since AB is equal to 1, if I have a word like ABBA, this will be equal to, AB is 1, so this will be equal to BA. Let's AB or AAB will be AA. AB will be 1. So A power I, B power J times, or let's say A power 10, B power 11, B power 11 times A power 15, B power 16 will be, this will be B times, this will be B, so this will be squared. So if I have, if I have A power 12, B power 6, A power 10, B power 5 will be, this will be A power 6 times, this will be A power 5, so this will be A power 11. So can you tell me what will be the words, how will a word over A star, so let me call it R star. What do you mean by R star? So if R, let me call it R bar star. R is a symmetric binary relation, then R bar star is the reflexive transitive closure of the relation X A Y X B Y for A B in R. Okay. So if R is a symmetric binary relation, then R bar star is a reflexive transitive closure of the relation XAY, XBY such that AB is in R and XY is in S. Okay. Now let me state a proposition we are going to prove. Proposition: R bar star is the smallest congruence containing R. Okay. So now this is what we are going to prove. So if R is a symmetric binary relation, R bar star is this is a proposition we are going to prove. So now this makes sense to say that A star, we are using star in two different places in two different ways. One is a reflexive transitive closure. The other is as clean star. Okay. I hope that's okay. So if you have A star quotient by R bar star will be can you tell me how words over this semigroup will look like? Anybody?
B power I, A power J.
B power I, A power J, such that Ij is in M. Yeah,
Yes, yes.
you are right. Okay, now let's see why. Why is it B power I, A power J? And okay, I mean, that's not, how do we prove that it is actually B power I, A power J? You start with a long word and then you start reducing it, and then you will prove that. You can prove it by induction actually. Yeah, you can actually prove it by induction. All right, this semigroup, so this semigroup, let's keep it here. This semigroup is called A star tilde R bar star, or let me just, so this one I'm going to denote this semigroup by this notation. Okay, angle bracket AB and AB equal to 1. Okay, what is the meaning of this notation? So it is actually saying that it is it is obtained by taking the semigroup, taking the free semigroup generated by two generators AB and quotiented with respect to the smallest congruence generated by this relation AB equal to 1. Okay, is called bicyclic semigroup. Okay.
Sir, a quick question.
Yeah.
So when we have defined this R bar star,
Yeah.
do we require the XY to be in S1? Because I mean, if we want R to be contained in
Yes, you need it to be in S1. No, 1 second. Yes, you will need it to be in S1. Yes, thank you.
Okay.
Yeah, because otherwise it will be problematic, no? You won't have the relation AB. If S is not a monoid, you won't have.
Yeah, I mean, we won't know whether it even contains R.
Yes, exactly. So you need it to be in S1. Thank you. Okay. It's called a bicyclic semigroup, and another exercise. So this bicyclic semigroup can also be represented as pairs Ij such that Ij is in N. Yeah. So Ij stands for B power I, A power J. Another presentation. That's not necessary actually. Okay. Define the product operation in bicyclic semigroup. So find out what is the product operation in bicyclic semigroup. Okay, now let's come back to this R. This R. So this way of representing a semigroup, this will be our standard way of representing a semigroup. Okay, it's called a semigroup presentation. Semigroup presentation. Okay, so it will be like you will specify an alphabet and then you will specify a relation A R. Okay, A is an alphabet and R will be a symmetric relation. Since it is a symmetric relation, instead of putting a tuple, we will be using equality. You will say AB equal to BA, for instance. Yeah. For instance, you could say AB equal to BA. What does that mean? It means the semigroup is commutative. Yeah, AB equal to BA, A square equal to A, B square equal to B. If you have this, what will be the semigroup? Can you tell me? The semigroup generated by AB, generators AB, and AB equal to BA, A square equal to A, B square equal to B. What will be the words? What will be the elements?
This would just have epsilon and AB as elements.
Yes, it will have. So
Yes.
let's not. Yeah, so if you specify it is a monoid, so it will have one, which will be the identity of the same monoid. Then epsilon A, B, and what?
That's
And you will have A.
that's all.
Yeah,
AB or BA, one of
yeah, one of them. Yeah, one A, B. Okay, so that will be a semi-group presentation. Now let's try to prove. How do we prove this this proposition? If R is a binary symmetric binary relation, R bar star is the smallest congruence containing. The smallest congruence containing R is nothing but R bar star. How do we prove that? So let's call it proposition 1. So let's try to prove proposition 1. Okay. So what do I want to prove? I want to say that. So what is the meaning of this proposition? R bar. Why do I need to bother about this R bar star? So basically, what that proposition says is that in order to find a word, how do we find a word? Oh, you start with a word and then you keep on reducing it by applying the relation. That's what I did in this case. Whenever I wanted to find out what is a word, I started with the word and then I kept on reducing it by applying this rule AB equal to 1. And whatever I eventually got is my whenever I cannot reduce it any further, that's an element of my semigroup. Yes, that's what I was doing. So that's exactly what this proposition says. Yeah. So if you have a semigroup generated by R, if you want to find out the smallest congruence generated by R, all you have to do is you have to find the reflexive transitive closure of this relation xay, comma xby such that AB is an R. Okay. All right. So how do I prove that? So first of all, if R is a binary relation, if R is, so let's prove it this way. If the smallest congruence containing R contains R bar star. Yeah, that's obvious because the smallest congruence containing R must have, for every AB in R, it should have xay, comma xby, because it's a congruence. And then it should be closed under reflection and transitive closure because it's an equivalence relation. So therefore, the smallest congruence containing R should contain R bar star. All right, any question? Okay. So that's one part, that is the smallest congruence containing R contains R bar star. Now what you have to prove is that R bar star is a congruence. So if you show both these statements, then you show that R bar star is the smallest congruence containing the relation R. So how do we show that R bar star is a congruence? So basically you have to show that if AB is in R bar star, then X A Y X B Y is in R bar star. This is what you have to show.
It's 11 o'clock.
Yeah, this is what you have to show. Now, how do you show this? So since AB is in R bar star, that means that AB is in R bar star implies there exists some A0, or let's say U0, U1, U1, U2, etc. UK, UK plus 1. So is that U0 is equal to some X0 A, no, X0 so there exists a bunch of tuples, so such that U0 is equal to A and UK plus 1 is equal to B, and U0 UI plus 1 is in R bar. Okay. So this relation is what I call R bar. Okay. So R bar star is the reflexive transitive closure of this relation R bar. So R bar, what does it do? It just for every AB in R, it just couches it in some X and Y. Any questions? Hello? Is an R bar. Now UI UA plus 1 is in R bar implies that there exists some Xi Yi in S1 such that UI is equal to some UI is equal to some Xi Vi Yi and UI plus 1 is equal to, oh, I should use I mean, whatever I am writing is very simple. I'm just expanding the definition of what is R bar. So basically what I'm going to say is that UI is some word which is obtained from R by attaching an Xi and Yi to the left and right. So UI, let's imagine UI is equal to some Xi Vi Yi and UI plus 1 is some Xi Vi plus 1 Yi, and similarly for all these pairs. Okay, so from this what you can get is that, so basically you want to show that XAY XBY is also in R bar star. Yeah, that's what you want to show when you want to say that R bar star is a congruence. So what can you do? Can somebody tell me what can you do so that you get this this tuple? Any idea? Anybody?
Sorry, so what tuple do we want? I
So
mentioned this.
you have AB in R bar star. You want XAY, XBY in R bar star. So for some XY in S1.
Okay, right.
So basically what you're going to do is that
So we can multiply all the xi's and yi's.
you basically multiply each of these tuples by x and y on the left and right. Okay. So basically what you will say is that in order to get this, you will consider that we will show that x u0 y x u1 y etc. x uk y x uk plus 1 y is in R bar star. Yeah. So now, sorry, is in R bar. If you show that each of these tuples are in R bar, then it is clear that their transitive closure, which is xay and xby, is in R bar star. Now, to show that each of these tuples are in R bar, all you have to show is that x, xi, vi, yi, y, comma, x, xi plus 1, vi plus 1, yi, y is in R bar. But that follows from the fact that you consider x, xi, and yi, y for each of these tuples, and that will imply that if vi plus 1 is in R, therefore x, xi, vi, yi, y, sorry, comma, x, xi plus 1, xi, vi plus 1, yi, y is in R bar. Okay. Anyway, I think it's we got drowned in notation. Whatever the idea was very simple. Maybe you should try to. I should have given it as an exercise, but I have given already so many things as exercise. That's why. But try to prove it yourself. I mean, it's a very simple idea. Okay. All right. So that was about semigroup presentation. So when you have a binary relation R, you consider the smallest congruence generated by that binary relation, symmetric binary relation, and that will be that is nothing but the reflexive transitive closure of that binary relation. And when you quotient the free semigroup with that binary relation, you will get a semigroup, and that is a very convenient way of representing any semigroup. Okay. In fact, we will show that any semigroup can be represented that way. Okay, but yeah. Okay, so now I think we have all the ingredients we need for having our first jump to algebraic automata theory. Okay, so now let's go to languages. Okay, so I have a semigroup S. Okay, and so you will say that let S be a semigroup L subset of S. So you typically S is nothing but A star or A plus and so on, a free semigroup. But the definition we are giving is apart for any semigroup, not just the free semigroups. L subset of S is recognized by recognizable if A subset of the semigroup is recognizable if there is a finite semigroup T and a subset P of T such that there is a finite semigroup T, and I should have written, and a morphism H from S to T such that L is equal to H inverse P for some P in T. Okay, so what am I saying? So let's take the standard example, which is A star. I have the set of all finite words, and I want to say that L is a recognizable subset of this A star if there exists a finite semigroup T or a finite monoid T and a morphism H from A star to T such that L is nothing but H inverse of P. Okay, is this definition clear to you? Let's take an example. Even length words. Even length words. So I have A star here, and here what will I take? I can take the semigroup 0, 1, which is nothing but Z slash Z. Okay, and I have a morphism which maps all even words to 0, odd length words to 1, and that's my morphism H. And H inverse of 0 is equal to even length words. Okay. All right. Let's take another example. So let's take alphabet to be AB. I want to accept the set AB whole star. What is this set? The set of all words which is of the form AB, 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 and so on. Can somebody tell me what is the semigroup I should consider here? I want to accept AB whole star. Let's make simpler. Let's make A star B star. Okay. I have my alphabet is AB, and I want to accept the words A star B star. Can you tell me a semi group that can accept this language A star B star? Anybody?
We can do the same construction we did for B to the I, A to the J. Instead of AB equals 1, we will take BA equals 1.
You mean to say BA equal to 0?
B equal to 0.
Yeah.
Yeah.
Okay. So let's consider the semi group which contains 1. Okay. A, B, and AB and BA equal to 0. Okay. What is this semigroup? This semigroup has elements 1, A, B, AB, and BA equal to 0. What does this mean? If I have a word like ABA, what is the meaning? ABA is actually equal to BA equal to 0. 0 means it's a Once you have BA equal to 0 means what? Whenever I multiply, whenever there is a product with B followed by A, that will be a 0 element. Yeah. So what are the elements of, there are only 5 elements. One, A is, so what is the morphism? Let's write the morphism. Morphism H. H of W is equal to A if W is in A star. Okay. Or if my word is only composed of A, then it has value A. W is in B. If it is only B star, if W is only B. Okay. And if W is in A star, B star, it A plus B plus. A plus B plus. So the W will be AB. Yeah. Otherwise, is this clear or this example was too hard already? Shubham?
I think it's clear. Yes.
Clear? Okay.
Yes.
I think so, that should be W in A if W is in A plus and B if W is in B plus.
Yes, that is right. Thank you. If my word is only of A plus, then it maps to A. My word is only of B plus, it maps to B. And if it contains an AB, but it contains no BA, then it is AB. Otherwise, it contains B. So that is A star, B star.
And
Yeah.
here the epsilon maps to 1, right?
Epsilon maps to 1. Yes. 1 if W is equal to epsilon. Okay. Now, what is the accepting set? Set P. This accepting set P is, I want to accept this set A star, B star. My accepting set will be
1 A B A.
yes.
Everything except BA.
1 A B A B. Okay. All right.
Sir, is it helpful to look at H as the projection map from A star to A star modulo that relation, A1, A, B, B equal to 0?
Yeah, it is nothing but that, but I just wrote it by words. That's all.
Yes. Yeah. Okay.
So basically, whatever you have done is just taking A star and quotient with respect to the relation A B equal to 0.
Yes. Yeah. Okay.
Okay. Yeah, but I think we have to have an intuitive feel. Whenever we are given a language, we need to have an intuitive feel about what is the sense group which is going to be accepted.
Hmm.
You will learn how to compute it precisely. But right now, I just want to get a feel of what is. Okay, so we have already done one example. Now let's prove some standard proposition. So let's prove that proposition. If L1 and L2 are recognizable, then L1 union L2 is recognizable. Okay, let's prove this. So if L1 and L2 are recognizable, then L1 union L2 is recognizable. Yeah, just like the proposition, if L1 is regular and L2 is regular, then L1 union L2 is regular. Usually, how do you do that? You, in the case of automata, you will construct an automata for L1, you will construct another automata for L2. Then you will take their product And then you will say that this is a new accepting state and this is a new starting state of this new product automata, and that's how you do it. Let's try to do something similar here. So L1 is recognizable. That means that I'm talking about over the same alphabet, yeah, over the same semigroup. So L1 is subset of S and L2 is subset of S. Both of them are a subset of some finite some semigroup S. Okay. And I know that L1 is recognizable. So there is a morphism from S to T1. And so this morphism is H1. Okay. So there is a morphism from S to T1, and L1 is actually H1 inverse of P1. Okay. And similarly, L2 is recognizable. Therefore, there is a morphism H2 from S to T2, and L2 is equal to H2 inverse of P2. P1 is subset of T1, P2 is subset of T2. Okay, we get these two things. Now, okay, all right. So now what we can do, Saina, can you tell me what should be done?
Can we combine these two semigroups, T1 and T2?
Yes, we can combine these two semigroups, and that's called a product semigroup. Product semigroup. So how product semigroup? What is product semigroup? So if T1 and T2 are two semigroups, if T1 and T2, T1 cross T2, which is called the direct product, yeah, direct product of T1 and T2 is the semigroup which contains tuples A, B such that A is in T1 and B is in T2. Okay, and what is operation? So if I have A1, B1 dot A2, B2 will be, what will be the product operation?
A1, A2, comma B1, B2.
B1, B2. Okay, you just do the respective product operation. So it is actually dot 1 and dot 2. Yeah, if you denote the product operation in T1 by dot 1 and denote the product operation in T2 by dot 2, then A1 dot 1 A2 and B1 dot 2 B2. Okay, but we will not be writing dot 1 and dot 2 and so on. I just wrote it that way. So these kind of things are always assumed to be implicitly defined, yeah, because I take elements from A1, A2, so it should be from T1. So this is the product semigroup. This is a product semigroup. Okay, exercise. Yeah, you can verify that product semigroup T1, the direct product of T1 and T2 is a semigroup. Okay, so now I claim that there is a morphism S from T1 cross T2 to T1 cross T2. What is this morphism? This morphism, let me call it H. What does it do? So H of S will be the pair H of S, H1 of S and H2 of S. Yeah. So I can combine these two morphism, H1 and H2. And what does that new morphism does? It actually maps every element S in S to the pair H1S and H2S. So now you can verify that H is a morphism from T1 to T2, T1 cross T2, T1 cross T2, sorry. H is a morphism from S to T1 cross T2. Yeah, I'll leave it to you to verify. It's not very simple. It's very simple. Okay. So now, therefore, we have a product semigroup and a morphism H from S to the product semigroup. Now what should be my accepting set? So I claim that L1, we claim that L1 union L2 is H inverse of P, where P is equal to, can somebody tell me what is this new P? Can somebody tell me what is this?
Is it P1 cross T2 union T1 cross P2?
P1 cross
T2 union T1 cross P2.
T1 cross P2. That's
So,
it. Yeah.
so should it be P1 comma 0 union 0 comma P2?
Not every semigroup needs to have a 0. Okay.
Yeah. Okay.
Okay. So,
That's right.
and secondly, even if you have a 0, it may not work. The accepting set you are saying will not work.
Okay.
Um, we claim, okay. So how do we prove this? Exercise. So basically, how do we prove this? So basically, you want to say that you want to prove two directions. One you want to say is show is that L1 union L2. You have two directions. One you want to say is that is subset of H inverse of P. The other is the other direction. Yeah, L1 union L2 is the other inclusion. So here, yeah, you have to show two directions. Okay. And basically, what is the reason why it is so? Because imagine you have a word W in S. Okay, imagine you have a element W in S. Now under H it maps to H1 of W and H2 of W. Okay. Now if it belongs to P, that means that either it belongs to P1 cross T2 or it belongs to T1 cross P2. If it belongs to P1 cross T2, that means H1 of W is in P1. Since H1 of W is in P1, W is in L1. Okay. And if H2 of W is in P2, then that means W is in L2. So therefore, if W is in H inverse of P, it means that W is in L1 union L2. So that's one direction. If W is in H1 of P, then it means that H inverse of P, that means that H1 of W is either in P1 or H2 of W is in P2, and therefore W is in L1 or W is in L2. Now for the other direction, if W is in L1 or W is in L2, that if W is in L1 union L2, that means that W is in L1, in which case H of W1, H1 of W will be in P, therefore W will be in H inverse of P. And in the other case, if W is in L2, that means that H1, H2 of W will be in P2, and therefore W will be in H inverse of P. Okay, that's the other direction. Okay, so that is about L1 union L2. What about L1 intersection L2?
Same construction and just change the accepting set to P1 cross P2.
Yeah, you change the accepting set. P prime will be P1 cross P2. Yeah. So that will be the new accepting set for which L1 intersection L2 will be accepted. What about what about how do we prove that if L is recognizable, then L complement is also recognizable? How do we show that if L is recognizable, then L complement is also recognizable?
Just taking P complement should.
Yeah. So L is recognizable. So if I have a morphism from S to T with if L is equal to H inverse of P, then take H inverse of T minus P. T set minus P. This is all the elements in T which are not in P. H inverse of T will be L complement. Yeah. Because yeah. Okay. So we know how to do Boolean operations. Now, what are the other things to be done? The other things to be done are morphisms and inverse morphisms, and then concatenation. That we will do in the next class. Okay, any questions so far? Okay, I have to give you some exercises. Okay, so you have to show exercise. I'll just write it here. Exercise 8, 9, 10, and 4 in chapter 7. Yeah, is it chapter 7? No, it's not chapter 7, sorry. Chapter 2. Okay, in chapter 2. I mean, right now it's not necessary to submit, but once we do a little more, I'll ask you to submit something. Okay. All right. Any questions?
So, a general question: what will be the grading scheme for this course? Like, is this an assignment?
No, we will have exams, open book exams. Okay.
Okay, just exams or assignment. Okay.
Assignment, maybe I might give. I mean, you guys have to do the exercise. So right now, I'm not going to check the exercise, but maybe in couple of classes, I will give you an assignment to submit.
Okay. What about quizzes?
Yeah, quizzes will be there. 2 quizzes, one midsum,
Okay.
one.
Okay.
Okay. Again, it will be open book, and because anyway there is no way I can. I mean, I can do a proctored exam. That's also possible. But all of you have good net connection.
I mean, it's not stable always, so that is the issue.
But you can turn on the video. Yeah, all of you.
I guess we can try.
Okay.
But I mean, it's not always stable because I am using my mobile data, and which is not really very stable always. So others might also have this issue. So,
I just have to see you. So yeah,
yeah,
that's all.
yeah.
So maybe after I finish this chapter, these couple of, I mean, one chapter I have already done. So there are many things which I have skipped in that chapter. One is ordered monoids. One is ideals. Anyway, we will come once we get to Green's relations. I will do ideals again. So ideals I am skipping for the moment. Then there are some ordered semi groups. Some bit of things are there. Not all of it is necessary for us at the moment, for the moment. So I skipped some parts, but if you are interested in getting, I mean, they are good for you, building your intuition. So I would encourage you to read chapter 2 once on your own. It's not very difficult. A lot of things. Yeah. So I would encourage you to read that independently. That's one. Then once you finish this chapter, we can think of a quiz before we go into Green selection. So once we learn how to compute syntactic semigroups, we'll have a quiz. Okay. All right. Okay then. Thank you. See you next Wednesday.
Bye. See you.
Thank you, sir.
Yes.